Okay, so one more time about the course. So we must go to island, yes? So everything is up in the island, believe or not. So of course would be the course syllabus. And so, and then also the worksheet, yes, and then the notes. So let's take a look at the notes first, because it's talking. First thing I want to talk about is the chemistry, right? So before anything, before you can work on anything, you must understand the chemistry of experiment 2 first. Right. Now, what's experiment 2 about? What is experiment 2 all about? So, of course, how you learn and how you know is from the title, right? So let's take a look at the title on page 55. So the title is what? Weight loss and reaction mechanism. That sounds like same as experiment 1. So exactly the same thing. But the reaction is what? The oxidation of fructose in alkali solution. So this time you want to study the oxidation of fructose in alkali solution. So what's the Rayleigh law? What's the reaction mechanism or steps? That's okay. So let's take a look. So the reaction is fructose. That's the formula. C6H12O6. That's the formula. The structure is in the lab manual, I believe. So a little bit complicated. We are not too interested in the structure yet. So and then for me, I just abbreviate as F. F stands for fructose. In aqueous, in water, of course. Then we have with oxygen. Of course, the oxygen is in aqueous, so that means what is dissolved or soluble in water. Both are dissolved or soluble in water, aqueous, not oxygen gas. Then you form your product, and then you have your water. So that's your reaction. So what's the reaction step mechanism in alkali condition? So someone proposed the step would be 2 steps. Now, by the way, all of this is I copy from the lab menu. So, but you have it in ILA and also in the lab menu. But I just renaming the reaction equation, A and B, and then 1, 2, 3, 4. So someone proposed 2-step reactions. So first, the fructose react with the hydroxide, and then you form an anion, and then subsequent, the anion react with the oxygen, and then form your product. But you get your hydroxide back. So that's the reaction mechanism proposed. So it's not directly the oxygen react with your fructose. The oxygen is react with your anion. Now, few things we can talk about this reaction mechanism at this point. First, what's wrong you know, what if we want to study of this, what would be the trouble? Anything? Anyone? Is there any headache? What color is our photo? Do we remember? What color was our photo? Forgot, I know. It was what? Clear, no color. What about hydroxide? What color is hydroxide? Clear. What color is water? What color is oxygen? So everything is clear, no color. Can we study by using color to monitor? We cannot. You see? That would be a headache. Okay. What else we can comment? What's the function of hydroxide? What's the function? What is the hydroxide acting as?
Catalyst.
Catalyst. How you know? Why we say that? Why we say that? How can we tell? Well, I call it in and out. So the hydroxide come in, the hydroxide go out. So that's the definition of catalyst. Catalyst does not use up in the reaction. So it was there before, it will be the same after. Same before, same after. Wow, it's just being there. Is that funny? That's funny. That's catalyst. That's catalyst. And we haven't really talked about the how fast usually catalyst would speed up your reaction. Yes. But we don't know yet at this point. But it's in and out, so it's just being there. So that would be the definition of catalyst. So if we want to study and support this two steps reaction mechanism, it would be a little trouble. So people we design an experiment, or to support the two steps. So these are the following, would be the 5 steps. Of course, again, this would be from the lab manual, although I relumbering the numbers. All right. So let's talk about one by one. All right. First, reaction. So same thing, just like step A, hydroxide react with the fructose, and then you form your anion, and then your water. Questions to answer. Is this step fast or slow? Fast. How you know? I mean, either fast or slow. Of course. How you know? Did we do experiment? Yes, we did experiment. So that was task 2, I believe. So we put all 3 things together. So fructose, hydroxide, methylene blue together, and then you run the time it, and then you do the experiment again, but just the fructose and hydroxide first. Let it run for 3 minutes, make sure they got the anion, then you add the methylene blue. So the difference would be this step. So this is a little bit longer, so that one is a little bit faster. So we did do experiment to observe. What kind of reaction is this? What kind of the reaction? Any thought? You guys should have answered all this already, right? But what is fructose? What is hydroxide? What's hydroxide? What's hydroxide? What did we say? In alkaline, right? What's alkaline? Base, yes. Fructose, what's fructose? Where we find fructose? Where we can see and find fructose? In fruit, I guess. So do we eat fruit sometimes? Orange, apple, something like that. How does that taste? Sweet? Okay, yeah, of course we wish. But sometimes it's what? Sour? That's acid, right? What's the taste of alkaline? Huh? Bitter. Yeah, so alkaline is bitter. But anyway, so this is what? And then what do you have? Water. Acid plus base, what do you get? Water, right? So neutralization, acid, base. Are we good? Acid and base, you have neutralization, so you must have water and heat. Yeah. What about this step? Fast or slow? We say is what? Slow, right? How you know? Because your methylene blue plus, what color is your methylene blue plus? It's was it blue like this? So it was blue, yes? What color is your MP? No color. So we've been timing from blue to clear, yes? Why we've been timing that? Because it's slow. That's why we can time it. What about the type of reaction? What is this doing? This is MP plus. This is MP what? 0. Plus to 0 is what? Oxidation? Reduction. So this is reduction. Yes? Methylene blue plus to methylene blue 0. This is reduction. So this is what is oxidized? The anion oxidized. So yes, oxidation, reduction. So redox. Are we good? So we've been timing the methylene blue plus reduce. So this is a little bit, is this okay? So we've been timing this step. Yeah? Now what did we say in our title? Oxidation of fructose. Are we timing and monitoring this step, oxidation of fructose? No, we are monitoring what? reduction of methylene blue. You see? You see? Do we see it? Is that okay? Is that okay? It's okay, of course. So we would assume that's the that's the slow step, the rate determining step. So we would say that is the complement of of the oxidation of our fructose. But really, we are monitoring the reduction step of methylene blue. So I've been giving the analogy to students for years. So I say, if we're driving to school, San Francisco State, you use 19th Avenue, yes? You go south from Golden Gate Bridge, sooner or later you hit what? Holloway, right? But if you're in the daytime, do you guys know that if you drive on 19, 90% of the time in the day, there are police officers sitting, hiding it on Holloway Street. Do you guys know? Yeah. So, if you pass 19th Avenue, on 19 and pass Holloway, all of a sudden, people, officer pull you over from Holloway, yes, and say you went on red. You say, officer, you are on Holloway. How you know I am on red? You see what I'm saying? But can you say that? So what can he say is what? If he see red, you are green. If he see green, you're red. Or red is, you know what I mean. So, even though the officer is on Holloway, but he really is monitoring the 19. Of course, he could be on 19 Avenue, you see what I'm saying? But if he would be on 19, then he would be no business because everyone see him. All right, good? Yeah? So this is the argument. So even though he is on Holloway and he can still say you are on red. What about this step, fast or slow? Fast. How we know? How you know? Now we did not do experiment about this step actually. So what is this step about is from the oxygen in the air, atmosphere, and dissolve in the water. So this step better be fast, I say. Better be fast. Otherwise what? If this is taking too long, what happened? All the fish in the ocean would die. Better be fast. What about this step? Fast or slow? What color is this, guys? Clear. What color is this? Blue. What? Do you remember what happened? From clear to blue, was it fast, right? It was like instinct. And again, this is redox. What about this step? We did not do, and just fast. So, only one step is slow, which is the step 2, but in our lab manual is step 4. So this is our rate determining step. Yeah. So second step is our rate determining step. Now before we go further, just answer more questions. Number one, when we add all these 5 steps, do we get this step when we combine all the 5 steps? The overall, is it same as this one? Same as the first, our subject reaction, yes or no? No. What's the difference? The difference is oxygen gas, not oxygen aqueous. So this is oxygen aqueous, but when we combine this 5, we got oxygen gas instead of oxygen aqueous. So it's not the same, but is that okay? Are we okay with that? Yes. Huh? So when you combine all this reactant and then product, so you can get a piece of paper, put all this on one side and put all that on the other side. Then you try to cancel out whichever one you have on both sides. Yeah? After you cancel out everything, the leftover is this one, but it's oxygen gas. So it's not quite as this one when we combine the 5 steps. But is that okay? Yes, because this way is the oxygen gas, so we can shake it and then you can dissolve the oxygen gas back to the aqueous, and then you cycle the reaction again. So you can start the reaction timing again. That's why this time it's not like experiment 1 or other reaction. You time it once and then your reaction is dead. You have to get another A and B. But this time we shake it up, then we can do it again. We need to add more chemical. Okay? What's the purpose of hydroxide? I think we mentioned it already. What's the point of hydroxide? Guess what? Cat. What's cat? Catalyst. What about MP plus? Of course, it's what? Indicator. Remember, if we would talk about this 2-step, everything is clear, everything is colorless, no color. How are we going to study it? So we need to have the indicator. So we need to put in an indicator, help us, right? Just like the police officer hiding on Holloway, not on 19. That's smart, right? And also is what? Catalyst too. How come? Well, you take a look, the MP plus here, in and out, in and out. So that's the definition of catalyst too. What about oxygen? The molecular oxygen. What is the molecular oxygen? So that's electron carrier. So you take a look at the oxygen gas, become aqueous, and aqueous become the anion, and then get the electron transfer over. You see? So you're carrying the electron. So this is like carry the electricity. All right, so I think I answered all the questions. So one more time, the rate determining step would be step 2. I just be copying over here. Now, what's the rate law? So rate of the reaction would be change of photo over change of time equal to the K. Remember, it's always a rate constant. And then to your reactant. So this is your photo, but it's the photo anion, to a power of something, some reaction order, and then your methylene blue plus to another reaction order. So this would be very much like what we did in experiment 1. So change of photo over time always equal to a rate constant to your reactants, however many reactants you have, and then to some reaction order. So same thing, we have what? 1, 2, 3. 1, 2, 3. 3 unknowns, so we need 3 equations. Now further, what is photo anion in here? What is this guy? What did we call this? Intermediate. So we have an intermediate expressed in the rate law. We don't like that. We don't like that. We don't want. So what do we do? So we would go back to the first reaction, step 1. So step 1 actually is an equilibrium reaction. I didn't write equilibrium in here, but yes, an equilibrium reaction. So the equilibrium expression for this step 1 reaction, so would be photo anion over the photo and the hydroxide. Then we rewrite it. The photo anion is equal to K equilibrium photo and hydroxide. Now we can substitute this back to here. I tried the color and hope would be clear. So when we substitute the anion back to the rate law, so now the rate law is equal to K, the rate constant and equilibrium constant and photo and hydroxide and methylene blue. Now we all these are the initial concentration we know is no more intermediate. So that's your rate law. Rate law of what? What's TH? Theoretical. So all this mechanism is based on theory. So this rate law is theoretical rate law. But we did the experimental. So the experimental, what did we do? We only changed and studied the photo and hydroxide, but assume methylene blue plus is a constant. So we assume it's a constant, or it would not matter. So you would say this is 0 order. So the methylene blue plus concentration does not matter. to our reaction. That was the assumption. And so therefore the experimental rate law would be fructose and hydroxide only, not have the methylene blue plus. While the theory, we say the methylene blue may affect our reaction rate. So, are these two the same? Are they the same? No. So this is 3V, this is 6. They are different. They are not the same. How you to be the same? We need to prove, we need to do experiment and to prove methylene blue plus is in fact doesn't matter. But we did not do this experiment. Okay? So I think that's the chemistry.